Hi, this is Rhiyan from AGHAMALAYAN, and today we will be discussing about the gas law. So here's the first problem. You observe that a 30-liter container of ammonia has a pressure of 15.6 kilopascals. What is the volume of ammonia if the pressure is reduced to 12.9 kPa? Assume that the temperature is constant. So first, let us identify the given values. We are given the first volume, which is 30 liters. Let us label this as V1. We are also given the first pressure, which is 15.6 kilopascals. And lastly, we are given the second temperature, which is 12.9 kilopascals. We are also told that the temperature is constant and the volume and pressures are given, and that gives us an idea that the gas law that we will be using in this problem is the Boyle's law. We are required to find the second temperature when the pressure is 12.9 kPa. Be careful in labeling these values. These subscripts must be the same if they are related. So we are required to find the second volume, which is V2. And the Boyle's law indicates that the pressure is inversely proportional to the volume with the formula P1 times V1 is equal to P2 times V2, and by manipulating the formula to get the volume 2, divide both sides by P2, and we are left with P1 times V1 over P2. And by substituting the values, P1 is 15.6 kilopascals, V1 is 30 liters, all over by P2 is 12.9 kilopascals. So V2 now is 36.3 liters. So the new volume would be 36.6 liters, and as you can also notice, the pressure was reduced, the volume increased. This shows that the pressure and volume have an inverse relationship, as what the Boyle's law stated. So let us proceed to the next number. Number 2, calculate the new temperature if a container with a 6 liters gas at 90 kelvins is allowed to expand at 21 liters. So this time we are given the temperature and volumes of the air, and we are now going to use the Charles law by listing the given again. So the first volume, V1, is equal to 6 liters. The temperature 1 is 90 kelvins, and the second volume is 21 liters. Remember to always convert the temperatures into Kelvin before computing. In this case, we are already given a temperature in Kelvin so that we can proceed to the next part. Be careful in labeling these values because the subscript must be the same again. So the second temperature is missing, and by using the Charles law, the volume is directly proportional to the temperature. Thus, we have the formula V1 over T1 is equal to V2 over T2, and by manipulating the formula, cross multiplication, isolate the T2, so we must divide both sides by V1. So cancel, and we are left with V2 over T1. By substituting the values again, we get 21 liters times 90 kelvins all over by 6 liters, and that the temperature temperature 2 is 351 kelvins. If you notice again, as you increase the volume, the temperature also increases, and that explains Charles' law. So let us now proceed to the third problem. At 30 degrees Celsius, Dylan's backup oxygen tank has a reading of 850 millimeter mercury before he jumps in the lake containing methane. After diving down, the pressure in the oxygen tank reduced to 270 millimeter mercury. What must be the temperature below the lake? So the values are different again this time. Let us now list the given, which is P1. The first pressure is 850 mmHg. Temperature is 30 degrees Celsius, and lastly the pressure 2 is 270 millimeter mercury. Oops, this must be P1. So we are required to find the second temperature. And again, always remember to convert the temperatures into Kelvin. So you need to add 273 to it, and we are going to have 303 kelvins. So from the statements above, we can now tell that the law to be used is the Gay-Lussac. It states that the pressure is directly proportional to the temperature, thus the formula P1 over T1 is equal to P2 over T2. The formula can also be written the other way around as long as you put both the volumes at the denominator and the temperatures at the numerator. So manipulating the formula gives us P1 times T2 is equal to P2 times T1, and we need to isolate T2, so divide both sides by T1, and T2 is now P2 times T1 over P1, and by substituting we will have 270 mmHg times 303 kelvins, and all over by 850 mmHg. This will give us the second temperature, which is 96.2 kelvins. So this is the second temperature. Again, when the pressure drops, the temperature drops as well, and it shows the direct proportionality of the pressure and temperature. So let us now proceed to the fourth question, which is another gas law. A curious student wants to know how many moles a 35-liter stack of oxygen at 310 kelvins if it has an internal pressure of 200 atmosphere. In this problem, we are given the volume, temperature, and pressure. We are asked to get the number of moles of the container. Therefore, we must use the ideal gas laws, as it is the formula which contains all of the four values. So let us first list the given values. Volume is 35 liters. Temperature is 310 kelvins. Pressure is 200 atm. We are required to find the number of moles. So N is unknown. By using the ideal gas law equation, which is PV is equal to nRT, we manipulate it by dividing both sides by RT to isolate N, which is the number of moles. So we are left with N is equal to PV over RT. R is the universal gas constant, which is 0.0821 LATM all over by mole K. So let us substitute the values. 200 ATM times 35 liters all over by 0.0821 liter atmosphere over mole K times the pressure 310 kelvins, and the number of moles would result to 275 moles of gas. So for the last problem, in a birthday party, you were asked to add more helium to a 2.25 liters balloon that contains 0.12 moles of gas. After air was added, the balloon has now a volume of 3.28 liters. How many moles of gas does the balloon have? So in here, I listed down the first volume, which is 2.25 liters, and the first number of moles, which is 0.12 moles. After air was added, the volume, which is V2, 3.28 liters. We are now asked to find what is the new number of moles after the volume was increased. Therefore, we must use the Avogadro's law to relate the moles and volume with the formula V1 over N1 is equal to V2 over N2, and manipulating it in order to obtain the number of moles. So V1 times N2 is equal to V2 times N1. Divide both sides by V1. Cancel, and you are now left with N2 is equal to V2 times N1 all over by V1. And by substituting the values, V2 is 3.28 liters times 0.12 moles all over by V1, which is 2.25 liters, and the N2 would be 0.14 moles of gas. So when we increase the volume, the number of moles also increase, and that explains the Avogadro's law. So thank you very much for watching. Please like and subscribe to our channel at AGHAMALAYAN. Thank you.